Yeah.
Thank you for inviting me for giving this talk. I will present some of the results I was working on with Professor Nalewajko, who is my PhD supervisor at the Nicolaus Copernicus Astronomical Center in Warsaw. The outline is I will going to talk about four issues that had the common context. So I will start with talking about a very curious feature which is called HST1, which is a feature in a relativistic jet actually observed and highly variable. Then I will talk about the study of another flaring activity in the high luminosity blazar 3C454 and then some more theoretical considerations of the confinement shocks. I covered the energy dissipation efficiency and the polarization. I will start by giving a general introduction on what is reconfinement shock, using a result of simulation made by Peruccio and Sociano. You can see here three images showing the distribution of the mass density, the pressure, and actual velocity of a jet, which is simulated in an axisymmetric hydrodynamic code. This paper was concerned on the microquasars and how the jet would be confined by actually the stellar wind. But you can see here the basic idea. So we have a jet which is originally it has high density and high pressure, and it's relativistic, as you can see from the scale. And these are conditions in which it will first expand, not interacting very strongly with its surroundings, because it is overpressured. So its initial expansion is approximately conical, but as it expands, both the density and the pressure is decaying. So at some point they will be lower than the values in the surrounding medium. So then this jet is starting to filling actually the interaction with the medium is now getting to be seriously affecting the jet, and the interaction is mediated by very long oblique shocks, which eventually end with the strong collimation of the jet, and at some point the shocks can end in a specific point. At this point, as you can see there is a strong system of shocks which have a very complicated nature and you can see they are again overpressured in relation to the medium, but we also expect that at this point they may be also more turbulent and highly variable. And so
basically just collimating
right.
by surrounding pressure?
Yes. Okay. So I will now turn to the first, to the most interesting object that has been connected to the structure. So this is a jet of galaxy M87. This is actually the first jet discovered in extragalactic sources. This is a new ultraviolet picture made by Hubble Space Telescope. It shows a couple of features, and here is a radio image. It is a very broad image of the jet structure, and then using the VLBA observations, we can find this feature, which was labeled after the observations by Hubble. So that's why it says HSC1. This feature is shown here in magnification, and the radio structure is seen. And what is very interesting is that we observe superluminal motions, but it's clearly not a single source that is just traveling, and we observe it as a superluminal. It is rather a stationary feature which emits a series of consecutive blobs. So they were first observed by comparing the Hubble images, and the apparent velocities measured is about 6 times the speed of light. And then there were also VLBA studies made, and actually a little bit lower apparent velocity of 4 times the speed of light were detected, originating from the same point, but actually this VLBA structure is much shorter than this one. Okay, but what is the most spectacular about this feature? This picture corresponds to the one shown before. It was made in 1999, and so this was just rather not very. I mean, it was not so spectacular source, but in consecutive years there was some flaring activity. It started just about this time, and the brightness of this source was increasing till 2005, and at this point this source outshines the galaxy nucleus by a factor of 4. After 2005, we have seen a gradual decay of it, So this is something we have never seen before in any such in any specially resolved jets. And
I think one have to add that you would not see it. Because
right,
it's
because
so close that in all the other sources,
right.
this
So
is very nearby,
so
it will
so
be
so
visible.
the separation between the nucleus and HST1 is 0.8 arc seconds, about 0.8 arc seconds. So that's why it is resolvable in Hubble images. It would not be resolved. It will be barely resolved in from the Earth-based observatories, and but luckily it was also resolved by Chandra. And here, the image is much worse, but you can still measure the flux and get a very high quality light curve in the X-ray band. So this is the latest picture of the light curves compared in free bands. So you can see X-rays, near ultraviolet, and radio. And they are normalized to the peak, so we can see that they move fairly simultaneously. And the increase in the flux is dramatic. So it's about a factor of 50 increase from start of observing program. And in the meantime, this source was detected in very high energies. First by Hess. These are average flux detected by Hess in consecutive years. And what is interesting, but maybe not very well statistically significant by itself, is that during the maximum of here the green curve is the Chandra data. During the maximum of the flare, the TV flux was much higher than in other years. And at the same time, you can see that this, for comparison, flux of the nucleus is shown, and it's not changing at all. So,
sorry, the error bars of S here are not sigma. Yes, yes detection.
Yeah, it's 1 sigma. But this is actually in this year it was highly variable, and you have to add that the variabilities on the time scale of a few days were also detected. I mean, the few days it's a doubling time for the TV flux, and this highly constrains the size of the source, which I will show just in a minute. But on the significance map, or actually the map of the axis of TV photons, you can see that there is no actually way to say what is the actual source. The variability arguments, from the variability arguments we have estimation of the source size, which is 6 orders of magnitude smaller than the PSF of has.
So which one is the nucleus of galaxy? Bright
so you can
flaring source is
the
in low energy.
okay, so this is a kiloparsec scale jet here, and so the nucleus it's indistinguishable here in this image. Okay, so there was a debate about the origin of the TeV mission and also about the nature of the flares in all these bands. So there are some points that can be made. So first, that this M87 galaxy is not a blazar. There is the jet inclination to our line of sight is not very well known, but it is estimated to about 30 degrees. So actually, high Doppler boosting is not possible in this source. We can estimate the gamma, the Lorentz factor of the jet from the superluminal motion. So, well, that's certainly not the case that we can see this radiation highly boosted.
But sorry, but the HST1 does show motion towards in our direction, relativistic motion. Yeah, it has.
So because we see superluminal motions,
Yeah.
but this source that seems to be the origin of the sources, so it's consistent with being stationary, but it's like a fixed point through which some variable features are going through, and that's.
But they go to our direction because we see northern velocity, northern sea, right?
Yeah. But this is consistent
Yeah.
with 20 degrees and Lorentz
But to
factor
have
on the order of
a
50.
high Lorentz,
Okay.
have a high Doppler boosting, you need to have the inclination angle, which is comparable to 1 over Lorentz factor. So it's not really the case here. Okay, so we have different constraints on the size of the source, and from imaging, the highest resolution obtained by VLBI imaging, we have a 0.15 parsec as the limit on the radius, is upper limit on the radius of the source. And from X-ray variability is order of magnitude lower, and well, as I said, this is this Doppler factor here. But from the TeV variability, if it is producing the same position as the, for example, X-rays, is another order of magnitude more strict. There is a more strict constraint. And because of this, it was initially very. There were many doubts if it is possible that TeV emission could originate from the source, because, as I said, it's very far away from the nucleus, and well, you actually need a very high collimation is needed for that to be the case. But on the other hand, this simultaneous high state in all the bands from radio to TeV are suggesting that well, it should be considered. So there is rather no problem with the mechanism of the radiation, as was studied by Łukasz and other. So if we assume that we have a synchrotron emission that is responsible for the flare in all the bands from radio to X-rays, So then we can so then we can consider inverse Compton scattering on the electrons that emit in this bands, and the photons could just originate from their surroundings. For example, it could be stellar emission that would be Comptonized to produce a TeV flare. So mainly the only reason for dating the origin of this radiation is this size of the source, which is needed. But also there were many more scenarios proposed, but specifically trying to explain this TeV emission from the vicinity of the central supermassive black hole. But there is a big problem of opacity actually, and well, this debate is not already settled, I would say. Okay, but so about this object, HST1 would be would originate in the collimation of the jet by the ambient medium, and because of its angular separation, we can estimate that it happens at the distance of about 100 parsecs from the source. And here I will discuss the study of high luminosity blazar in its also very well-known and covered outburst, and show that it also requires that the emission originates rather far from the central engine. In this study, this flare also is a coincidence that it happened in 2005. Here is the radio, not radio but optical light curve, and for comparison the radio flux is also given here by this gray line, and there was a multi-wavelength campaign that was covering the object in X-rays and multiple optical bands, near infrared, and also radio. But in these initial studies, there were no millimeter data available, and we included them in the studies and think that they are very important for modeling the radiative processes here. So here are millimeter data in two bands, and they show a very similar behavior. Actually, we have this data. They are shown here connected, but we have no data from this period because of the proximity of sun, just above the maximum of the flare. But then there are a lot of points that are covered here, and so we think that this is the actual peak of the millimeter photons, but the peak of optical emission is not very well known because of this gap in the data. But there are arguments to there are arguments to think that these millimeters, millimeter data are actually showing us the true bolometric variability of the synchrotron emission, whereas the optical data, since their spectrum is very soft, so they are very close to the high energy cutoff of the synchrotron emission, and so we so there is a reason to suggest that we should because the millimeter data they are shown here with green points. We only have these 2 points from the maximum of the curve. Their spectral index is very specific, because if we first look on the broad band modeling, based first on the quiescent state there was a model constructed based on synchrotron emission and external radiation quantum. We have very good constraints on the electron photon index based on the harness of in the X-ray, and during the flare in 2005, these are the blue data. So the X-ray spectral index has not changed significantly, and so we are can very sure that the electron spectra here are consistent with P equal 2, and so the synchrotron spectra which are in the fast cooling regime should be flat. And in this picture we can see that the millimeter data show the spectrum average between flat spectrum of the synchrotron and absorbed spectrum, which has a spectral index 2.5. And so we say that we have a very firm estimate for the position of the self-absorption characteristic frequency, which is given here in dependence on the source parameters. And as you can see, it is a very powerful tool, because it depends very slightly on the flux level at this point, which we can measure, because we take it from the observed flux, and even it is even less dependent on the magnetic field strength. But so we can estimate the source radius, the emission zone radius. So emission zone radius is very large, and assuming that we model it as in the conical approximation, assuming that the opening angle is 1 over Lorentz factor, which is Lorentz factor was assumed to be 20 in this source, because we wanted to keep the synchrotron self-Compton emission on the low level, otherwise it would significantly soften the soft X-ray spectra. So we estimate the position of the emission zone at 10 parsec, which is much further than in the studies that were not including the millimeter data. And the previous studies were actually giving estimate which was 2 orders of magnitude lower, and this is rather inconsistent with the position of the zone, which is estimated on sorry. Okay, so this is the point that shows the estimate of the position of the emission zone, assuming there is a very crude estimate based on in the scenario when the internal shocks are involved.
Sorry, I'm just confused. This one, this zone is emitting the flares.
This is so if the flares would be connected to the internal shocks.
So observationally,
we estimate
you
zone
know the location.
in which there is energy dissipation connected to the internal shocks, and it could we know that the actual emission should be rather co-spatial with the position of the place where the energy is dissipated. So this estimate is 2 orders of magnitude lower. And okay, so that's basically why we think that another dissipation mechanism should be considered for this particular flare, and particularly because of its rather large variability timescale. The variability timescale estimated for our scenario, in which we place it at 10 parsecs, is about 1 month, but it could be actually higher, and it's observed on the timescale of 3 months. Actually,
This
so
gamma 20 is consistent with the superlunar motion, and with
this gamma is
and observing from 30 degrees.
In this source we observe superluminal motions with apparent velocity of 15 times the speed of light. So this is a bit higher, but of course from the superluminal motions we only have the lower limit on the Lorentz factor. Okay, let's maybe skip this because so then okay we decided to study jet reconfinement in the rather simple model in which we calculate the geometry of the position of the shock and the compact discontinuity, assuming something on the unshocked matter state. Basically, we assume that this is a spherical fireball, which could be for which we take a Lorentz factor and the total power involved. It could actually be have some internal energy, but internal energy would also decay, increasing, actually accelerating the jet, and at some point it would be well, rather insignificant for the unshocked state. And so this matter eventually crosses the shock at some point, and we calculate using exact shock jump equations how it could be deflected. Also, there is the energy balance requires that there will be assuming pressure behind the shock. We can compute other parameters, and get the direction of motion, the Lorentz factor of the shock matter, and also its internal energy. And the broad parameters of the model are the opening angle, and also important parameter is the position of this reconfinement. Okay. And so the position of the reconfinement can be estimated analytically. It was done by Komisarov and Fale in '97. You basically, because very little is known about the distribution of external pressure, so you assume the power law with some index, and so the solution.
So what's the origin of this external shock pressure? What producing this?
So well, this is very poorly understood. We rather have very little constraints on the state of the external medium, especially in AGNs. If we consider this scenario in GRBs, it's rather easier because we can have we can take a pressure distribution in the progenitor. So
Krzysztof, I must say I completely don't agree, because these are the parsec scales, hardening parsec scales we see directly in X-rays, the ambient medium in host galaxies. For my estimates for M87 in 2006, I took the data.
yeah, I know. Okay, so
This is just
you
the
don't-
pressure of the interstellar medium on this case. And
yeah,
you
but
observe it in X-rays.
you had data on the scale of 100 of parsecs, so it's but this is a a long discussion how to actually estimate this index, because of the difficulties in modeling the matter distribution in the most central parts of the galaxy. Of course, I mean it depends on the galaxy models, right? The elliptical galaxy structure.
But you see X-ray thermal emission very clearly, and you resolve it. And so you know the temperature of the gas, because this is a Bremsstrahlung emission. You know precisely temperature. You know the profile, so you can estimate the thermal pressure of the ambient medium relatively precisely. And this is this is what people are doing for elliptical galaxies because of the using Chandra like massively, right? This is like the big deal in
Yes.
clusters and elliptical galaxies.
But the point is that I'm not aware what is the accuracy at the parsec scale actually.
So observed pressure is good enough, strong enough to confine?
Yeah, so Łukasz showed that the pressure distribution, which is estimated from elliptical galaxy gas distribution and dynamics, is considered with this position at 100 parsecs in the case of N87.
So how much energy in the surrounding?
It's
It means external pressure in some sense hot. It means it carries some energy.
so the value proposed is 10 to minus 2 is it's rather typical, but it depends on this. I don't want to rather discuss it now because
I just
want
want
to show
to
you
kinematics, that
that
energetics.
how
Just to
right.
So in the center of elliptical galaxy, the number density of the gas is 0.1 particle per cubic centimeter, and the temperature is 10 to 6. So this is what is inferred from the X-ray observation, and this is true for every elliptical galaxy. So that would be the pressure.
But okay, anyway, know that how position the scale of reconfinement depends on parameters of it only depends basically on the jet power and the external pressure. So it is really a question of the energy, how energy in the jet compares with the energy density in the medium. Recollimation, okay, is possible if this eta is lower than 2. And well, there is a question how this estimate is how well is it how good is it, because the external pressure that we can measure actually is the pressure.
Sorry. It's,
Yes.
Before you were saying that you can, I mean, in the case of gamma reverse, where the pressure and the ambient condition are different,
Right.
at what scale do you expect the nozzle to be? Okay,
I'll show you in a moment. Okay. But okay, there is a question if the external pressure, which is somewhere here, it can be modified. It can be a bit modified because of the need for the matter to move on the curved trajectories. So you expect for this that there is a pressure gradient across the shock zone, and actually the pressure which is just behind the shock surface should be lower than external pressure, and the factor how much lower it is, it can affect these estimates, but well, it's so this may be a source of discrepancy if we can well compare these scalings. I want to mention that I think that okay, calculating many models of this kind, we calculated the total or let's say average energy dissipation efficiency, and our finding is that it depends on actually on one parameter, which is the Lorentz factor times the opening angle. So if it is lower than 1, then the efficiency is not very high, and actually behaves can be approximated with the scaling shown here, which is about 6% in the case of this parameter equal to 1. Then it integrates very fast. So this, I would say, are the confinement shocks that are not that much relativistic. But in the case when you have this parameter higher, of course this distribution could not just continue like this, but you find that very high efficiency of dissipation is in principle possible for these structures. So you can compare it to the efficiency of internal shocks. Here is an approximate estimate for high Lorentz factors, and so it depends basically on the ratio of the two Lorentz factors. These are Lorentz factors of two blobs that collide. The one with higher Lorentz factor is colliding with the one which was emitted earlier at lower Lorentz factor. So to have a high efficiency of dissipation, you need a
So
rather
two guys have
significant
the same mass,
ratio.
for example.
Excuse me?
Two blobs have the same mass.
It's yeah, this is assuming the same mass. Of course, having a different mass ratio, it would be different. But this is just for illustrative comparison. Actually, this is a in both cases, this efficiency could be much lower if we take into account that internal energy or magnetic field can make the shocks weaker, and so the dissipation would be less efficient. But okay, maybe show you one thing that I found interesting about GRBs, and you might find it interesting too, because recently there was a paper showing a very large simulation of a jet breaking out of the GRB progenitor in the this actually is intended to model long GRBs, and this is a hydrodynamic simulation which was okay. So Morsen and Bagaman have before simulated the actual breaking out of the progenitor star. Now they have continued this simulation to very high state to obtain actually the state of the opacity going down. So the photosphere would be now the photosphere radius would be reached. You can see that from the scale that they continued the jet as far as 60 times the stellar radius, and they showed that there is still a interaction of this matter of the jet with the matter. It continues very far beyond the star radius, and here when they show the actual this is the same picture as here, but in the other color scale, you can see that a large reconfinement structure dominates this state. Then they have calculated the profile of Lorentz factor and energy on the axis, because they assumed axis symmetry. And so you can see here the ratio of internal to rest energy, which initially, as long as we are inside the unshocked matter, it decays fairly similar to the prediction calculated for a spherical fireball. But at the point of recollimation, you can see a very strong shock. Here is the Lorentz factor, which was initially it was growing because of acceleration due to the energy conversion. Then it was at the value of 400. After the shock, it dropped very significantly, of a factor of a few, and at the same time there is a lot of now internal energy and hot electrons that try to cool down, but they are again heated again and again in the series of the reflected shocks that continue to be present further away. And so So I would say that indeed an efficiency of dissipation at this whole structure is indeed very could be okay in these assumptions, of course, could be very high and can actually be well produce a population of hot electrons that would continue to this point. And they calculated opacity, and they show photospheric radius, so it is of the order of this the size of emission of emission. And here is the light curve they produce. So I added this picture because I was thinking about your comments that well the light curves of the GRBs are not really not reproducing the in the simulations, but these authors claims that this is a good example of the light curve, but they actually stopped simulation because they reached out of the simulation box.
So it is basically kind of internal shocks, this emission is
The
Confinement shock.
requirement, but some you
internal
say
shocks.
that some shocks bouncing around.
Okay, so internal shocks are actually present here, and this is the zone when this emission is produced. But first, we don't see emission from here. But when the electrons are heated in the place, so they rather keep their energy, because you can see there is not much decay in the internal energy of the electrons. So they can keep their energy, maybe because they are not so the adiabatic losses are not so very.
But why it's electrons? Electrons probably would cool, but I mean, if you have energy in protons,
Because this is hydro
Protons.
simulation, so they are just
so they don't know.
heating. They don't know.
It's
It's just
just
hydro simulation.
Right. So of course they point to the fact that no internal effects are studied here, but well, you may actually I don't know what you would say about this result. So I would actually finish at this point. I prepared also the polarizations results, but I have no time, so I don't want to keep you. So
okay.
Thank you.
Thank you.
If I can come back, so just to this made sense. So when you said about the pressure profile, I think it's exactly the opposite. That in gamma reverse we don't know really the pressure profile. And that
Okay,
was also a discussion with Giancarlo made the comment, right? We're presenting his studies, right? He said you said that you can
I skipped this slide which shows studies by Brombeck and Levinson, and they were calculating collimation, but in two cases, I mean, in the context of GRBs, they calculated collimation by static medium and by winds. These simulations show that collimation, of course, if it is produced in the interaction with the winds, it has a double structure. Okay, because there is because basically you have here a double forward and reverse shock, which are tilted. But when the medium is static, okay, you don't actually have this one. But I would say that because this simulation runs very far away out of the star, so there is would be very hard to estimate the profile of the pressure here,
I mean something different.
because this is very dynamical.
But in general, exactly, in gamma because this is unknown, and you can put many things here. While if you study sufficiently large scale in AGNs, we know it because the pressure profile, because we know it from observation. So,
Okay.
for example, when we proposed this reconfinement shock scenario for M87, we took the jet power, which comes from the energetics on the large scale, the lot that we see. So there cannot be a lot like factor of few on the uncertainty, and this is the 10 to 44 hec per second. And the ambient medium from the X-ray observation of the interstellar medium, and then the position of the reconfinement shock is this 100 parsec. So you cannot really move it. You don't have much freedom, right? That's why we were so excited about this. So I don't think that in AGNs this ambient medium profile is that unknown. I think it's actually pretty good, well constrained. This is just one comment.
Okay, I agree.
You are right that here. I mean, but this energy, I think, in this the density and the profile in this simulation is something that they get up from stellar cones or something like that. So it's a completely different scale. So
Yes.
it's a completely unknown fact. I agree with you. But I wanted to ask you: is this somehow a way to make the outflow discontinuous, right? Which is a requirement for.
Well,
Yeah,
there
yeah,
is
yeah.
a big question of is the injection of matter here from the initial central engine is it variable? There are a lot of effects that would change this picture very much. In the case of variability, I guess that their assumption is that they have a constant flux of.
But also in the case of a constant flux, the fact that you can have after the first reconfinement point, you can have other shocks, reconfinement points. In a way, it's like breaking up the continuity of the outflow if it is continuous, right?
Yes, because
It's not doesn't come out from here, but it's a question if it is possible to break up after what is that 1.5 10 to the 11. If you can have something.
It's really hard to say. I mean, the situation here when the emission is actually calculated is very complicated, and even in this very simplified simulation, I think only such simulations, but continued much further, would settle such questions.
And I have said a very basic question, because I at this point. The fact that the Lorentz factor after the reconnection point rises up, what is it? Yes.
So you can see it moves in accordance with the decay of the ratio of internal energy to the rest energy, and this is actually predicted by the spherical fireball scenario. This is.
My question is that you get the energy from the shock, from the such shock. Is that right?
So
to bring to reaccelerate
for acceleration is
yeah.
Yes, this internal energy
You get
is converted to the energy, kinetic energy of the ordered flow.
But it
That's
is possible.
the same things happens here, and actually the authors they as the initial parameters they take let's say this ratio of energies equal to 80, which is like this, and initial Lorentz factor of 5, and according to these parameters, the value of the Lorentz factor achieved is 400, which is because it's basically a multiplication of these factors. So that's what are the initial conditions that are assumed. But this is a very well known effect. I mean this acceleration because it's Blanford-McKee paper on the fireballs.
This one is just thermal acceleration, right?
Yeah.
And compared to spherical case, just shock convert kinetic energy to just internal transfer, eta is larger and gamma is smaller.
Yes, yes, exactly.
But how at this stage possibly this this material is optically thick, I guess.
Yes, it's optically thick all the way here, and they calculate.
How they evolve? They still hot, really.
Right. So these plots show this is the photospheric radius, right? So it's calculated, I guess, on the axis. This is how it evolves with the time. This is observed time, actually, including all the light travel effects and so on. It changes a bit, but I would not tell what is actually, and they don't also discuss what are the actions of these fluctuations. This value 2.5, it's 2.5 times 10 to 12. It's actually this, so it's rather requires that this is in the further stages, right? But they also calculate, because this is what they calculate is the black body that is emitted from a relativistically moving source. So, this is the observed temperature of radiation. It's the order of 200 keV.
So that stays optically thin, right?
And